Hello everyone, we're Team91. Here we are going to present our design agents for the Azul game. The first step is to determine the characteristics of the problem. We find there are generally four main characteristics worth considering in the war game. First, the actions within the game are deterministic, as the action will always result in the same successive state in the same round. The initial state is stochastic. The tiles drawn from the bag are random and the first player is randomly chosen for the first round. The game is adversarial. Both our agent's goal and the opponent's goal is to maximize their score and to have the score higher than the opponent. Lastly, we have perfect information about the state. All the information related to the game state, grid, patterns, tiles in the factory, tiles on the center of the table are visible to both players. In terms of all four characteristics mentioned above, temporal difference learning, minimax, and multi-color research are implemented.
Now let's move on in more details regarding temporal difference learning. The reason why we believe this will be successful is because TD learning automatically learns weights for each action through training. Both action and space weights are large, so we represent each state with 30 manually extracted features and choose the best action. These features are mainly be associated with our score after action is taken, number of tiles on each row and column, and whether our agent is the first agent. Finally, we need to set the training configuration to make sure the weights can be updated on a large number of episodes. What we do is to write the feature as an attribute and keep track of it in a lawfare. There are multiple drawbacks with respect to the agent. Firstly, we have not defined any action space and state space, which makes our feature vector very difficult to converge. Besides that, the opponent's action will affect the learning seriously as we are training against a greedy agent. From the weights of features which are found to be important in many games, they are not very distinct between all features.
The minimax algorithm inherently incorporates adversarial situations where each player tries to maximize their reward and minimize the opponent's reward. Since Azul is an adversarial game, and we have perfect information about the game state, we decided to try it out for our game agent. We have implemented alpha-beta pruning combined with heuristic pruning to reduce the search space. We also implemented dynamic depth so that as the game progresses, the agent is able to look further into the future. Our thresholds for different depths are based on the number of available actions in the root node, which might hinder our ability to fully exploit the 1 second time limit.
So we aim to implement MCTS to fully exploit the 1 second time limit. We first implement a vanilla version of MCTS. For every turn, we abstract the current board position into a node representation, then start the MCTS. We incrementally build up the tree by repeating simulation with 4 steps in the iterations: selection, expansion, simulation, and back propagations. Once we have reached the time limit, the simulation stops, and thanks to MCTS being an anytime online policy, we are always going to find the moves by looking for the children of the root nodes with the highest Q value. However, this has many limitations. For example, we use random to expand and simulate. This will misguide the tree to simulate a lot of bad moves, therefore no guarantee in the Q value to converge. So we use pruning and minimax with depth of 1 to guide our simulations. This way, our tree is at least simulating possible moves and our Q value can converge.
But after implementing the upgrades, MCTS still didn't get the expected performance. This is likely due to the fact that we build a new tree every time in every turn. And the Q function we use is a simple Q table. This causes our tree to do a lot of recomputation that significantly increase the time for the Q value to converge. And due to the tight time limit of each term, our simulation is likely to stop before good moves are found. And because of the low robustness, even though our MCTS has around 50% win rate against our best agent minimax, we choose to submit our minimax because it's more consistent, as MCTS might lose to weak agents. Here we can see that we are demonstrating the minimax agents versus the MCTS agents. And yeah, in this game, minimax is doing pretty well. And MCTS, like I said, might not found a good moves before time limit stop. So here's why MCTS is losing this time. But it might happen that it found good move and it beats our minimax. That also happens. So if we have more time, I would like to implement subtree optimization and incorporate reinforcement learning to pre-train a Q function to guide our selections. In this way, the MCTS retains the information for next turn, and using the guidance for the pre-trained Q function can do a lot more meaningful simulation, so good moves can be found quickly. And yeah, so right now our minimax loses, it wins our MCTS.